All right, the next speaker is Andrew Craig from the University of Johannesburg, and we're going to lattice theory now. So he's going to talk about dual digraphs of finite semi-distributive lattices.
Thanks very much, and yeah, thanks to the organizers for putting on such a good conference. So these are the two co-authors. Many of you will know Miroslav, or you can see him, and Jose started working on this after finishing his honors. He had a few months to kill before starting his masters in Sweden. So yeah, he's been an important part of the project. So this is roughly how the talk's going to go. I'm going to spend quite a bit of time on the dual representations of finite lattices, because I think it's quite it's probably quite unusual for many people to see for the first time, but it's also quite fun, and there's some it's nice to sort of see the pictures and see how it all works there, and then we'll move on, and hopefully I'll have a chance at the end to say some things about where we're headed. So the basic setup, we're going to be dealing with finite lattices, and the main kind of machinery here are going to be using filter ideal pairs. So it's just some familiar definitions. A filter is an upset closed under meets in the lattice, while an ideal is a downset closed under joins. What's going to be useful for us is the fact that in a finite lattice, it means that a filter can be simply written as a principal upset and an ideal as a principal downset. And what we're really going to be using are what are known as maximal disjoint filter ideal pairs. So the name kind of explains it all, but it's useful to see a few examples as well. So the basic idea, you've got a filter and ideal that must be disjoint. We're also going to require that they're both non-empty. And then they must be maximally disjoint in the sense that you can't extend either of them without then not having a filter or not having an ideal. So the two on the right, you can see that the element that is left out there, if you were to try and include that in either the filter or the ideal, then you would not get a disjoint pair. The 1 second from the left is not maximal in the sense that you could make the ideal bigger or make the filter bigger to include more elements. Some other quick definitions, just some reminders. An element will be join irreducible if whenever it's the join of two elements, then it must be equal to either of them. And what will be useful there is that join irreducible elements have a unique lower cover. And then when we start to look at these at the disjoint filter ideal pairs, the meet of the filter in a finite lattice is going to be join irreducible, and the join of the ideal part will be meet irreducible. And then we also have these equivalent conditions, and really the interesting bit here is the third one, when the union of the filter and the ideal gives you the whole lattice. So you saw the one on the far left was an example of that on the previous slide. And then these equivalent conditions we'll need to make use of in the proofs. So those are a kind of special kind of filter, maximal disjoint filter ideal pair. And where this all comes from really is from work by Ploszczyca from the mid-90s. I'll just give the sort of vague outline of the setup that he uses before we look at some examples. So in order to set up a dual representation, he takes the dual space to be the set of all these maximal disjoint filter ideal pairs. His setting is actually slightly different, but it's equivalent. So let's just talk about the maximal disjoint filter ideal pairs. He then puts a binary relation on there and a topology, and talks about having graphs with topology. And then the lattice is then recovered as a set of maximal partial E-preserving continuous functions from that graph with topology to the two-element poset with the discrete topology. For us, we're not going to worry about topology at all because we're in the finite case, and so it plays no role. For those who are familiar with either Priestley duality or Urquhart's representation, Ploszczyca is a generalization of priestly duality and really just another way of looking at Urquhart's representation. So this is the main takeaway for us from that, is that we're going to take a lattice and then the set of maximal disjoint filter ideal pairs, and then we equip it with this binary relation, or if you want to, we'll refer to it as a set of arcs, where a pair is, one pair is related to another if the filter part of the first pair is disjoint from the ideal part of the second pair. And you'll notice that this gives us a reflexive binary relation in our graph, or you can think of the digraph as having loops. So here's our first example. Obviously, when you have a setup that is used for all lattices, not just distributive ones, you look at the simplest non-distributive lattices. So what do the maximal disjoint filter ideal pairs look like on N5? Well, here's one of them. So that gives us one vertex in our dual digraph. Here is another, and then this will be the third maximal disjoint filter ideal pair. So we've got 3 vertices in our graph. And then when we add the arcs, we use the rule from Ploszczyca, and we get this, we get the digraph drawn at the bottom. So 2 important things to observe. Notice that this is not transitive because we don't have an arc from AB to CA. And also notice that two of the maximal disjoint filter ideal pairs here, their union gives us L. So the first and the third one, those are what we'll call sort of total maximal disjoint filter ideal pairs, because their union is the whole lattice, whereas the one in the middle, there's an element left out. The other non-distributive lattice of interest is the modular lattice M3. And just very quickly, you can kind of see what happens here when you do the maximal disjoint filter ideal pairs. You can do it in each of these 6 ways, which gives us 6 vertices in total. The arc structure here then becomes quite complex. We end up with these kind of double arrows around the outside, and then 3 cycles in the inside between particular vertices. So those are kind of 2 nice examples to get us started. For those who are familiar with this, if you don't know about or you haven't seen before Birkhoff's representation for finite distributive lattices, then don't worry. But just to reassure you that if you do restrict to the distributive case, well then this edge set or arc set is simply going to be give you a partial order on that set of maximal disjoint filter ideal pairs, and so then you can recover Birkhoff's representation theorem. I've stated it here in the kind of perhaps the most familiar way for those who've seen it before, but it is the way that we're going to recover the lattice is going to be equivalent to what is done here from the 1930s. So how do we recover this lattice in the general case when we're not looking at distributive lattices? The lattice is going to be recovered by taking the maximal partial edge preserving maps from this digraph to the 2-element poset, and we'll denote that lattice by a backboard L. And I'll just quickly do an example here. So we had N5, and we saw that its dual digraph was this 3-element digraph here. So now we're looking at maximal partial edge preserving maps. So, and from this digraph into the 2-element set with its usual order. So the 2 kind of obvious ones are if you map everything to 1 or everything to 0, that certainly preserves the relation. The next 2 obvious ones are if you take AB to 0 and the other 2 to 1, or if you take AB and BC to 0 and then just CA to 1. And then the interesting one is really where the maximal partial story comes in. And that's if you map AB to 1 and CA to 0, and then you're stuck. Okay, you can't map BC in that case to either 1 or 0, and so you simply have to leave it out and end up with a domain that is not the entire vertex set. And then using the ordering, which is the pre-image of 1, you then recover the lattice ordering. So that's how the representation works. And although Ploszczyca was not interested he was doing it for arbitrary bounded lattices, his theory does, when you restrict to the finite case, this is the representation that you get. Okay, so that's kind of the background to it. But we've ended up with quite a strange situation here where we've got the two simplest non-distributive lattices, and their dual digraphs are completely different. They're very, the one is a nice efficient representation, while the other one, you'll notice that there are actually more vertices than there were elements of the original lattice. And Ploszczyca observed that, in fact, for M3, you can even represent it with a different graph. So this was some work then that Miroslav and I did with Maria Gouveia, and that was to identify exactly, well, to characterize exactly the graphs that are the dual digraphs of finite lattices. It's a bit of a strange name. We call them TIRS graphs. The basic idea is that this binary, if you think of the arc set as a binary relation, then you have a separation property. You have this property which is kind of called reduced. And then the TI condition is really a weakening of transitivity. So in the distributive case, you would get transitivity, but now that is being weakened. And from that, in the case of finite lattices, we're able to get this representation theorem. We get a one-to-one correspondence between finite lattices and these finite TIRS digraphs. Right, so then we wanted to see, well, that's a very general description because it's covering all finite lattices. How can we provide descriptions of other classes of not necessarily distributive finite lattices? And we end up looking at semi-distributive lattices. So these are the conditions that define join semi-distributivity and meet semi-distributivity. And these are some examples. So the one on the left is join semi-distributive, but not meet semi-distributive. And then if you flip it upside down, you get the opposite occurrence. And what's quite interesting here is that N5 is going to be both, whereas M3 is neither. And I should also just comment that actually what got this started was a Latrobe algebra seminar where I was sitting in Joburg attending a seminar in Latrobe, and the speaker was from Hawaii, and he made some comments about semi-distributive lattices, which got us kind of interested in this. So what happens to the maximal disjoint filter ideal pairs? Well, if L is joined semi-distributive, then that will be the case if and only if, when you've got these two maximal disjoint filter ideal pairs, basically what it's saying is that each ideal is attached to a unique filter. And the sort of heavy lifting in the proof is done by this characterization theorem of joint semi-distributive lattices that says if you've got a meet irreducible, then there is a unique minimal element of this set here, the set of elements K and L. And so what's important here is the fact that right at the beginning, I said that the join of an ideal in one of these maximal disjoint filter ideal pairs will be meet irreducible. And so having that relationship enables us to get this first result. And then a more general result. So here we don't have to restrict to finite lattices, but what it's saying here is that your out neighborhood of a vertex in a dual graph, the out neighborhood will be equal if and only if the filter part of those vertices is equal, and then dually for in neighborhoods and the ideals. So what this gives us is a theorem about the dual representation of finite join semidistributive and finite meet semidistributive lattices. So I didn't spend too much time on that definition of the TIRS graphs, but there was the property S there, which was a separation condition, which said that if you've got two vertices, then either their out neighborhood must be different or their in neighborhoods must be different. And what happens in the semidistributive case is that join semidistributivity forces one of those to be the case. Meet semidistributivity forces the other case. And then, of course, when you've got semidistributive, which has both join and meet semidistributive, then it's saying that it's not a case of an or, but an and, that both the out neighborhood and the in neighborhood of every vertex must be different. So here are just some examples. On the right, you'll see the dual digraph of N5 that we constructed at the beginning. And then we've got these two other lattices which satisfy one but not the other condition. And if you stare at them for a bit, you'll be able to see that indeed their dual digraphs do satisfy the condition given in the theorem. So that was nice. And then we started to see something else happening in these dual digraphs. So here's a definition that some of you might be familiar with from graph theory, that if you've got a digraph, a subset of the vertices is going to be a dominating set. If every vertex not in that set is seen by a vertex from the set S, right? So there's an arc from some vertex in the set S to every vertex not in the set S. So here are some examples of dominating sets from some of the digraphs that we've seen already, with the elements of the set S given in red. And what we're going to do is we're going to say that an element of a digraph is transitive if whenever you've got an arc from X to Y and an arc from Y to Z, then you've also got an arc from X to Z. And what happens in digraphs, and again here this result doesn't require finiteness of the lattice, but when you go to the dual digraph, the transitive vertices are exactly those maximal disjoint filter ideal pairs where the union of the filter and the ideal gives you the entire lattice L. To get to where we want to go, we're going to need this other sort of result from lattice theory, that if you're a finite join semidistributive lattice, then all of the co-atoms are meet prime and dually. And so what this gives us is this result that says if you've got a finite TIRS graph and you're dual to a finite join semidistributive lattice, then the transitive vertices of G will form a dominating set. How does the proof go? Well, if you take a vertex in this digraph D, then you can think of it as a maximal disjoint filter ideal pair because of the representation theorem from before. Then, because we require that the ideals are proper ideals, we know that Y is not going to be the top element of that lattice, and so therefore there must be a co-atom above or greater than or equal to Y. And then, because of the lemma on the previous slide, that co-atom is going to be meet prime. And now remember that the total maximal disjoint filter ideal pairs, the joins of the ideals are meet prime and the meets of the filters are join prime. And so using that meet prime C, we can then form a maximal disjoint filter ideal pair that will be total and therefore will be a transitive vertex, and it will satisfy this condition that there is an arc from this vertex to U. We thought initially that this would be an if and only if statement, but it turns out that the case of transitive vertices forming a dominating set happens if and only if we've got a finite lattice in which every coatom is meet prime. I'm a bit short on time here, so I'm not going to spend too long on this, but there's a kind of a dual concept in graph theory of an in-dominating set, which is kind of exactly what you would expect it to be. And then if you combine both in-domination and usual domination or out-domination, you get what's called a twin-dominating set. So when you have meet semi-distributivity, then you get the transitive vertices forming an in-dominating set. And of course, then for finite semi-distributive lattices, we're going to get the transitive vertices forming a twin dominating set. And then I don't really have time to say anything about this, but we're kind of just scratching the surface of starting to understand these dual digraphs of finite semi-distributive lattices, and there are many directions in which we are still keen to head and to explore some of these different possibilities. And then here are a few references, and with that, I'd just like to say thanks very much.